Hi again, everybody, and welcome back. This example with the skateboarder is another good example of conservation of energy. Now it's going to be sort of in two parts, as indicated by the A and the B right here. But remember, the conservation of energy is the assumption that all the energy initial is going to be equal to all the energy final. That's kinetic initial plus potential initial being equal to kinetic final plus potential final. All right. Now this with this skateboarder right here, the skateboarder is moving at base level. Right. We can call this base level right here, or call this level 0. All right. But he or she, can't really tell. They have long hair, but whoever it is, he or she is does have some energy because they have some velocity. Well, what happens is the skateboarder kind of hits the ramp or the half pipe or quarter pipe, I guess, and they go up. And as they go up against gravity, gravity does negative work on them so that their kinetic energy decreases, but their potential energy increases. So they're going to go up and reach some point where they actually stop in midair. They're no longer moving. And of course, you know what's going to happen. They're going to hopefully turn around, but they're going to come back down and hopefully hit the ramp and come back down safely. All right, so I'm going to do this in two parts, which means I'm going to take this whole segment, this whole problem right here, and kind of move it up into the corner a little bit like that. So I got a little more room to move, or to draw. All right, so A right here. All right, find the height of the ramp. So H is what we want to solve for. Now we have three positions right here. And instead of saying initial and final, what I'm going to do is say position 1, position 2, and I'm going to draw it over here. Position 2 and position 3. All right, so when we talk about the change between 1 and 2 and 2 and 3, it won't be confusing if I say initial and final, because 2 is the final of the first half, and it's the initial of the second half right there. So I'm just going to call it 1, 2, and 3. All right, let's find the height of the ramp. So we're going to say that the energy at 1 is going to be equal to the total energy at 2. All right, all the energy at 1 equals all the energy at 2. We're ignoring friction. All right, we're assuming there's no energy loss due to friction right here. This is a very, very smooth ramp, we'll say, with a smooth rolling skateboard. And we want to find that height of the ramp. All right, well, energy 1 is going to be K, kinetic initial, plus potential initial. And energy 2 is going to be K, oops, I meant to, well, it looked like ones. I said initial, I meant 1. The final potential energy, the final energy is going to be the potential energy of 2 plus the kinetic energy of 2. And that's a problem with doing initial and final when you have three different parts right here. So between here and here, the energy should stay the same, but the type of energy is going to change. So that means 1/2 K. I keep wanting to say kx squared. That's very similar to the spring work, right? Now we want to have mv squared, right? mv at 1 squared. Plus, all right, what is the potential energy of this skater down here? If we call this base level, then we say they have no kinetic energy, or no potential energy. I'm sorry, no potential energy because mgh, they do have mass, they are experiencing gravity, but that's going to be 0 because h is 0. We're going to set that equal to, call that mgh1. mgh at 2, that is the top of the ramp right here, plus the kinetic energy at 2, plus 1/2 m velocity at 2 squared. So we have our initial kinetic, our initial potential, our kinetic at 1 and our potential at 1, and we've got our potential at 2 and our kinetic at 2 right here. We should be able to solve for the height of this ramp because everything else we know. All right. Which, by the way, I should write some of these things down. The mass of the person equals 55 kilograms. Okay? And the velocity at 1 equals 6.5. meters per second. And the velocity at 2 equals 4.1 meters per second. So we have all that stuff. Okay. Let's see if I can move this around. Nope, I don't want to do that. Thought I could move around that. Getting a little crammed in there, but that's all right. We got our knowns. That's actually all we need to know. The mass, the initial, the velocity at 1 and the velocity at 2. Let's turn that around and solve then for the height at 2 right here. What I'm going to do is I'm going to just I'm going to go straight across, I think. So A will be on the bottom and B will be up here. All right. So we're solving for this height at 2, which means we're going to have to subtract over 1/2 mv at 2 squared to this side. So that means 1/2 mass velocity at 1 squared minus 1/2 mass times the velocity at 2 squared equals mg h, h being the height at 2. Let me draw a little better 2 there. Okay? Well, even though we know the mass of the skateboarder, nice thing about this is that the masses cancel out, so it shouldn't really matter. And if we want the height of the 2, right here, we're going to solve for height, all we have to do is divide by g. Divide by g, so that means solving for h, I'll put h first here. H is going to be 1/2, or 1 over 2g, well, and I'll put it underneath 1/2 initial velocity squared divided by g. I guess I could just put in v initial over 2g, but I'll do it this way. Minus 1/2 velocity at 2 squared over g. That's going to be our equation for the height of that ramp right there. All right? So let's put in our values and find out what we get. So it's going to be 1/2 times, what's our initial velocity? That is 6.5, right? 6.5 squared over 9.81 minus 1/2 final velocity, that is 4.1. 4.1 meters per second. Ooh, squared, right? We need to square it. Squared over 9.81. And what you could even do, and it might even make a little more sense to do, is you could factor out the 1 over 2g. That might make more sense to do as well. But either way, this works for us. So our height is going to be what? I get that our height, that is the top of the ramp at point 2, is 1.3 meters above the ground. All right? Above the original position, that is the baseline right here. All right, so 1.3 meters going up just like that. All right, now this is going to help us to solve the second part. The second part asks, what is a skater's maximum height above the ground? All right, I'm going to draw a line to kind of separate these out right here. All right, and the maximum height above the ground, part B, I'm going to draw in blue. All right, so that's part B. The maximum height above the ground. So we'd like to find the h, or the height, that is, at position 3. H at 3 equals what? How high do they go? All right. Well, if you know anything about somebody's maximum height, and we hopefully remember this from projectile motion, the maximum height above the ground, especially if you're moving straight up in the air, your final velocity is 0. All right. So the velocity at 3 equals 0 meters per second. All right, and we should also write down that the, let's see, what's the velocity at 2, because we're comparing 2 and 3 right here, right? The velocity at 2 was 4.1 meters per second, and the height at 2, we just solved for that, that was 1.3 meters. We can also write down the mass of the skateboarder as well. We have it written here too. But as you recall from last time, it's very possible that that may just cancel out. So we'll see what happens. So we're comparing now the energy at 2 and all the energy at 3. So that means the kinetic, oops, I meant to put a 2 there. We're comparing the kinetic plus the potential at 2 with the kinetic 3 and potential at 3 right here. All right, position 3. So we're moving from here to here. Here they are starting at some height, but they're also moving. Here they're at the maximum height, but they're not moving at all. So, kinetic at 2. So we've got 1/2 mass, velocity at 2 squared. By the way, I'm taking this and kind of moving it, shifting it down here. All right. Plus, what's the potential at 2? The potential at 2. That's mgh at 2, right? And they do have some potential energy because they're starting like part way up the ramp right there, or at the top of the ramp. All right. Equals kinetic at 3. 1/2 mass times the velocity at 3 squared. Hey, we know what's going to happen to that, right? What happens at the highest point right here at 3? The velocity is 0, so that goes away, or will go away. Plus the potential energy at 3. Here's our potential, and of course that is mgh of 3, and that's what we're solving for. Okay? So, what can we get rid of? Aha, as predicted, all these have mass in them, right? mv squared, mgh, 0, and mgh right here. So all the mass can go away. It can go away. All right, because they all cancel out. And all we need to solve for now is the height at 3 right here. Well, we do that by dividing this whole side by g. So that means, let me switch back to blue here, 1/2, not a very good 1/2, is it? 1/2 velocity at 2 squared plus gh, with the height at 2, divided by g is going to equal our height at 3 right there, our maximum height above the ground. And again, our height is with reference to the ground right here, so that's what we want to solve for. Okay? So, let's plug in some values, and we'll see what we get. So 1/2 times, what's the velocity at 2? Position 2 right there. It's 4.1, right? 4.1, and that's going to be squared. Plus 9.81 times our height at 2. What's our height at 2 right there? That height we solved in the last part, right? That was 1.3 meters. 1.3. All divided by 9.81. 9.81 being g. And this will solve for our height 3 right here, which if we plug in our values, what do we get? And I get that their maximum height is 2.15, or I'll just say 2.2 meters above the ground. Let's draw that a little bit better. 2.2 meters above, not above the top of the ramp, but actually above the ground, because our reference point is that the ground is 0. This is 1.3 meters, and now they're at 2.2 meters above the ground. So all the kinetic energy right here that they had, this is all Ke at this point, becomes all potential energy. Oh, you know what I did? Now, I sometimes call kinetic energy Ke. I'll just say all K. All K right here. All your energy is all K, and this is all potential right there. We'll use the actual symbols. But between any 2 points, as long as you look at the difference in kinetic energy and difference in potential energy, you should be able to find what your unknown energy is, and therefore maybe what your unknown velocity is, or what your unknown height is, which is what we just did. Okay, so that was a good example of conservation of energy. If you have any questions, please make sure you see me. But in the meantime, thanks for following along. See you on the next one.